Okay, so I will go to this idea of how do we find S. So how to find S. So the answer is in the gradient. Okay, so the one word answer is just gradient. Okay, let's start with a very simple example. So suppose f is a one-dimensional function. So R1 to R1, okay, 1D function. Suppose del f by del x1 or df by dx1 is at a given point, right, is let's say 5 at given point. Right? So intuitively what it means is that if I increase x1 slightly by epsilon, then f is going to increase by 5 epsilon, and if I decrease x1 by epsilon, then the function is going to decrease by 5 epsilon. So that means that this is not really, I can't say for sure that this is an optimal point or not. If I'm minimizing, then I would like to, then we would like to decrease, right? So then we would like to decrease x1, right? And this is my direction, right? So that means my s, direction s is -1, right? Remember, I am in one dimension. So my direction is to reduce x1, which is -1. So suppose x1 was 0, I was at origin. So then x2 would be 0 plus some alpha times -1, right? So then I just have to decide what would be a good alpha. Okay, let's extend this to let's say 2 dimensions or maybe 3 dimensions. So suppose f is let's say 4x1 square minus minus 4x1 plus x2 square. Okay, and if I look at the gradient of f, this would be 8x1 minus 4 and 2x2. Okay, and let us say I am at point let's say 1 1 at 1 1. So in our course, all vectors, x and gradient, they are all column vectors. So we will try to write them as column vectors as far as possible. So this gradient of f at x1, we can denote it as, this might be confusing, so I will just write it as 1. Okay, this is, so superscript 1 means I am at the first iteration. So at the first iteration, my gradient is going to be 8 minus 4 is 4, and 2 times 1 is 2. So what this gradient is suggesting is that if I increase x1 slightly by epsilon bit, I will see a plus 4 epsilon change in the function. So that means I would like to decrease x1, and I would also like to decrease x2. So it really is a good indicator of which direction should I go to. Okay, so so s -1 -1 might be a good direction. because the gradient is pointing towards plus, and this is telling me that the function is going to increase. The sign tells me that it is going to increase, and this number tells me how much is the increase. So it might be a good direction, but also other directions which have negative values here might also be okay. For example, let's say -2, -1 might also be okay, and let's say -7, 0. This might also be okay, right? What about this direction? Let's say s equal to -1 and +1. Okay, would I see some improvement in the function if I move in this direction s? Yes, because I would get a -4 epsilon sort of improvement and +2 epsilon of addition. So overall, it might be okay moving in this direction. So this is also good, right? So also okay, right? So these are all descent directions, right? So we will a direction of descent. So I would say a descent direction is a direction where, so this is very roughly speaking, right? So don't tell anyone that I taught you this, because I'm going to be very rough here. A direction where the function decreases in the neighborhood, right? So if you move a little bit in this direction, you should see a decrease. Okay. So how can you check whether a function is a descent direction or not? Okay. So so this is where the Taylor series comes into picture. So first order Taylor series approximation tells us that f let's see, fx plus alpha s is equal to, let's say, at 1. So I'm at point number 1. So fx1 plus s transpose gradient of f at x1 plus higher order terms. And what the theory of Taylor series tells us is that when alpha is very small, as alpha tends to 0, this expression, right, this goes down to 0. So there's an alpha also. I'm sorry for missing this alpha, so note this alpha. So higher order terms, so the theory tells us that they are of order alpha square, or they go to 0 faster than this term, because this term is also going to go to 0 as alpha goes to 0. At alpha equal to 0, this term goes to 0, and these higher order terms also have alpha factors, alpha square and alpha cube, so they all go to 0. And at alpha equal to 0, this becomes a trivial equation. But the theory says is that these higher order error terms, they go to zero much faster than this term. Okay, faster than okay. And same is true with second order approximation. The third order term and the fourth, the higher order terms beyond the second order approximation, they tend to go to zero faster than this put together, this whole thing put together. So so in the neighborhood of in a very tiny neighborhood of x1, we can just say that fx it's nearly equal to fx1 plus alpha s transpose. This we can say, but we can also say is that if gradient of f, so this is a vector, so I can't say that the gradient of f is positive or negative because it has n terms in it. So suppose I say that grad f is non-zero, right? Is not zero, then the function has to change in the neighborhood. It can't remain the same because that's what the derivative is telling us. It has to change provided this gradient of f is non-zero, right? So this is a first small remark, and the second thing we can say is that if there is a direction S such that S transpose gradient of f of x1 is less than 0, okay, then there has to exist, right? Then there must exist some alpha in the neighborhood, or we can move a little bit in s direction, and definitely our function should decrease. Okay, and there must exist a point along s in the neighborhood. So sorry for the poor handwriting. This is along in the neighborhood of x1 such that f of x1 is strictly greater than, or the new point is better than so the new point is better than the old point. Okay, so this gradient is very, very important. Okay, this is the corner piece in optimization. If you understand gradients well, then you can do all optimization, at least the continuous part, continuous optimization. Discrete optimization is slightly different beast. We'll come to it towards the end of the course. But in continuous optimization, gradient is like everything, right? If you don't have gradients, then you are pretty much shooting in the dark. And if you have gradients, then you have some light to work in. So this part is very important, right? So any direction S such that S transpose gradient of F is less than 0 is a descent direction. You can go there. Okay. So there are some questions. So let me go back to the chat window. So Nakibur says, can we select S randomly or is there a thumb rule? So the answer is no. There are no thumb rules. There are no random things. There are precise rules for selecting S. Okay. So so let us see. So suppose I gave you gradient of F. So suppose gradient of S is known. So this is a question for all of you. Let's see who can answer. What is a sure shot direction in which so find S such that S transpose grad F is less than 0. So what could be that? What could be that S? One is you can go ahead.
Where the S transpose grad F becomes -1, that is the direction where there would be maximum decrease in the function, and should it be that one?
Right. So either you can look at the individual components of F, grad F, and based on the sign you can select S. But one sure shot S where you don't have to look anywhere is to
opposite to the gradient vector, sir.
Opposite to the gradient vector. Who said that?
Me, sir, Madhav.
Madhav. Okay. So Madhav says consider S is equal to minus of gradient of F. So then what does this term become? So this becomes minus of gradient of F transpose gradient of F. And what is this? This is just sum of squares. Okay. So this is equal to -1 into sum of squares. Recall that if there is any vector, let's say x1, x2, xn, or even some other terms, and I have x1, x2, xn, and if I multiply them, then it becomes x1 square plus x2 square plus so on and so forth. So this is just actually the norm of f, right? -1 into okay, and this is definitely negative. Okay, provided what? When will it be negative? Always, except at one point, at which point it will not be negative.
Norm is 0.
Yeah, except when grad f is 0. Okay, so if gradient of f is non-zero, it is always a good idea or always not a bad idea to go in the negative of the gradient direction. Okay, and this is called the direction of steepest descent. Okay. So direction of steepest descent is your minus of gradient of f. Okay, and why is it the steepest? And you can prove it formally. This can be proven that of all the directions, that you can take at a given point. This is the steepest in the sense that the rate of decrease is the highest in this direction. Okay, so you can set it up as a problem of finding the best possible S. So there's a question. So Kritika is clarifying that we don't have to go in the direction of the gradient, the opposite to the gradient. Okay, but saying opposite to gradient is so tedious that most optimizers will just say gradient. Okay, and expect that the whole world will understand that they want to go in the ulta direction. Such are professors, and they expect the world to understand that. So so the minus of the gradient is where we want to go. So opposite of the gradient is the steepest descent direction. Okay, and this can be proven. So let's go back to the Taylor series and see so see this approximation. So so if f of x plus alpha s is nearly equal to f of x plus alpha times what was it, S transpose gradient of f, and then I want to say that for fixed alpha, so I don't know alpha yet, so I just want this term to be as negative as possible so that I can go down as quickly as possible. But I also want S to be unit directions. So I want to minimize S transpose gradient of f subject to the norm of S is 1. And this is an optimization problem over S. I'm trying to figure out the best possible direction. Grad f is given, right? It is known at the current point. If you solve this optimization problem, you would get S star to be minus of gradient of f by the norm of, so that it becomes a unit direction. So if you are talking about the unit directions in which to go, and the direction where the rate of change is the highest, so then you should take this, right? It's a unit direction. Okay, and the proof of this is not too hard. It comes from geometry. You can imagine this geometrically and try to prove it, or you can do some, you can expand, you can write it as S1 times something and S1 square plus S2 square is all 1, and then try to prove that each component of S should be the negative of each component of F. Okay, so that can be shown pretty easily. We will not go there into that proof very formally, but just tell you that is true. So let's draw a contour and try to see its interpretation. So again, suppose some two-dimensional function is given to us, and this is a contour. That means this is a curve for f equal to constant. So f equal to, let's say, 2, right? So these are all the points where function is taking value 2, and suppose currently I am here. So if I draw a tangent at this point, the gradient vector will point in this direction, and what this result is trying to tell me is that we should go in the opposite direction of this. Okay. So this is something you should practice and try to understand. What is this tangent, and what is this direction, and what is this direction. Okay, but quickly I'm just going to tell you that this is the minus of gradient of f. Okay, and if you go perpendicular to this direction, so suppose you go in along this direction locally in the small neighborhood, then you would not see any change in the function. Okay, because you will be then moving on the contour of f. That means you will be moving along points where it is constant.